today I will be discussing about one of the darkroom experiment, that is grating spectrometer. So here our aim is to determine the wavelength of the light source, which is our mercury lamp over here, and additionally we will be calculating angular dispersive power of a diffraction grating. So the apparatus which we will be using over here is, first of all, is the light source, that is our mercury lamp, and this whole thing is called the spectrometer. There are various types of spectrometer. There is optical spectrometer, mass spectrometer, magnetic spectrometer, etc. But we will be using this one of our optical spectrometer, and we will be given a spirit level which we will be using during the experiment, and we have a diffraction grating, looks like this. We'll be mounting this over this holder. And for noting down the readings, we have given the magnifying lens. Basically, a spectrometer consists of 3 sections. This part is called the collimator. There is a slit at one end, and for adjusting the slit, the screw is given, and at the other end there is a lens, and the screw is used for focusing the slit. The second part of the spectrometer is this, which is called a circular table. It is commonly known as prism table, but here we will be using grating instead of prism, and it will be mounted over here using these 2 clamps. And third section is the telescope with the eyepiece. First of all, I'll put the spectrometer in a straight line to the source, and it should be as close as possible to the source. Now this collimator will make the light parallel to each other when it comes out from this part, and the light source is as at infinite in this position. Now this telescope is used to observe the image of the light, and it can be rotated on the either side on the vertical axis, and the rotation can be noted through these 2 windows. We will be noting the readings for both the windows, and over here we will be mounting the grating which I have shown you earlier. It looks like this. It consists of a large number of parallel slits of same width, but they are separated by equal spaces. Let's say there are n number of slits, and of same width, let's say A, and B is the separation width of opaque spaces. Then the grating element is given by G equals to A plus B, and for the slit which we will be using, you can see over here it is mentioned 15,000 lines per inch. So our grating element will be this much, that is given over here, formula in your manual. N equals to 1 by G. N is the number of slits per unit length, so we will be using the value, that is 2 into 10 raised to minus 3 for the grating constant. How it is coming? that will be explained to you during the session. Now suppose if a monochromatic light of say wavelength lambda passes through this collimator from the narrow slit and it is incident on the diffraction grating. We have not mounted right now, just we are assuming that it is passing through a grating, diffraction grating. So the diffraction pattern will be observed through a telescope and it will consist of sharp narrow lines parallel to the rulings of the grating. So these sharp lines are called the principal maxima, which is given by the equation G sin theta equals to plus minus n lambda, where G is your grating element of the diffraction grating and theta is the diffraction angle, n is your order of diffraction which you are observing, and lambda is the light source wavelength. So as you can see from the equation, this theta is dependent upon lambda. So instead of monochromatic light, if we have polychromatic light, then for each diffraction order will be having as many lines of diffraction as corresponding to the different wavelength of the light source. So basically grating, this grating which we use in the experiment allows us to determine the wavelength of various spectral lines of the light source with higher resolution, instead of we use the So this grating allows us to determine the wavelength of the spectral lines of the light source with more high resolution compared to the prisms. That's why we are using this grating instead of prism on the prism table. And one has to take care, this grating should be held from the edges only. You need not to put your finger at the center. And the other quantity which you will be calculating in the experiment is the angular dispersive power, which is given by the formula d theta by d lambda equals to n by g cos theta. There is a correction in the manual. D is not there. D is printed, which is incorrect. Instead it is n by g cos theta. So it's basically the rate of change of diffraction angle with the change in the wavelength. Now what happens over here, when we place the grating on the holder and light falls on the grating, the diffraction occurs at an angle. Now as you can see in the figure, light falls normally on the slit and different order of images are formed. Initially when we see through the telescope, we'll have the only this part, that is we are getting only white light, and on each side we'll be having different spectral lines. Because the central part, that is the normal, when the light falls normally on the slit, there is a lower intensity and the whole intensity is divided among all orders. So this particular light is known as white light and it is of the order 0 order, and since for all the wavelengths 0 order is same for all wavelength, so it is still in white in color, and on both sides this image will be having first order and second order spectrum. So we can measure wavelength for a particular light for a particular order, and we can take the average of that particular color and we can calculate the lambda for that light. Now as I mentioned earlier, we'll start with the procedure now, and as I mentioned earlier, we'll first of all align the spectrometer just parallel to the source, and we'll keep the spectrometer as close as possible to the source. And first of all, we need to adjust the slit to the narrowest position, and we'll observe that through the collimator first. So I'll use this screw for adjusting the slit, and for focusing that you'll be using this screw, and it will be look like this. The same thing we'll be observing through the telescope. This is the screw. This is the screw for locking and unlocking the telescope. So I'll unlock this slightly and move the telescope in a straight line to the collimator, and I'll lock this telescope. And now I'll observe the same slit through the telescope, and I'll make it as sharp as possible through this screw. So it will be looking somewhat like this. Now in the next step, we'll be balancing this prism table using the spirit level. You can see over here there is a bubble inside this. So you need to place this spirit level to the edges over here. There you can see 3 screws are there below the table. So you have to keep this spirit level in between any 2 screws, and you need to check whether this bubble is at center or not. Right now it's approximately at the center for these 2 screws. If not, then you will be adjusting these 2 screws to bring back this bubble into center. The same thing you will be doing for another 2 screws. So total 3 times you need to repeat this process, and when all the 3 sides are balanced, or you can say the bubble inside the spirit level is at center for all the 3 places, your prism table will be balanced. And next we'll be following a method called Schuster's method for aligning the spectrometer for the normal incidence. So for that, first of all, you need to take one reference reading for the alignment. So you can take readings from either of the window. So I'll explain you first how to take the readings. First of all, the LC of this spectrometer is 1 minute, which you can verify during your session how it is. There is a circular scale and a vernier scale, and this circular scale consists of degrees up to 360 degree, and on the vernier scale there are different division up to 30, I guess. Then we will note down the reading. Suppose you have 80, 81. So in between these two you have 85. So 80. Then there is one small line inside this, and there is one bigger line. So each of these small thing counts for 0.5, which if you convert will give you 30 minutes. So you will read that as 80 degree 30 minutes, 80 degree 30 minutes, then 81, 81 degree 30 minutes up to 85, and you will note down the vernier division which is coinciding to this scale. Suppose you have the condition like this. This is a vernier and it is coinciding to 80.5, 80 30 minutes, 81, and then something like that. So your scale is over here. So you will write the readings 80 degree, this is of 30 minutes, and then 81. So it is coming in between this. So we will note down the lesser one, that is 80 degree 30 minutes. Now it is not coinciding directly to the 80 degree 30 minutes. So in this case you will note down the vernier division which is exactly coinciding with the scale. So suppose 6th division of vernier is exactly coinciding, so we'll write down the reading as main scale reading MSR. Then you will write down the vernier scale division into LC. So this is your 80 degree 30 minutes plus vernier division 6th one is coinciding into LC is 1 minute. So this will give me 6 minutes. This 6 minutes will be added to this. So we'll have total reading 80 degree and 36 minutes. Now if your reading comes like this, this is a vernier scale and the main scale, it is exactly coinciding with 80 degree, then you need not to see the vernier scale. You can directly write down your total reading as 80 degree 0 minutes. Now for the Suster method, I will be taking from one of the window one reading that will be called as reference reading. It will not be required for the calculation, but for this alignment only we need to note down that, and depending upon that we'll locate the spectrum. So you can take the reading from either of the window. For my convenience I am considering this window. So right now my reading is approximately 85 degrees and 30 minutes. So we have taken the reading from this window, that is approximately 85:30. So we can say it is approximately 86 minutes. So now I'll rotate the telescope in such a way that it rotates up to this reading minus 90 degree. Or if you are considering this window, then you need to add that reading to 90 degree. So for this window I'll subtract that reading from 90 degree. So it is approximately 86 degree. So when I subtract that from 90, so we'll have 4 degree. So we'll rotate the telescope up to this. Now I'll rotate the telescope through that reading. So I'll unlock this and start rotating in this direction. So when you'll start rotating, this circular scale will rotate and you have to go up till your reference reading minus 90 degree for this particular window. So somewhat like this position you will reach, and at this position you need to lock the telescope. Okay. Now next we'll mount the grating on the holder using these two clamps. We will not touch the grating from the center, and this is a screw for locking and unlocking your prism table. So we'll unlock this and we'll start rotating the table towards the telescope in such a way that after a certain rotation we'll find the image of the light, that is the white light, which we'll be observing earlier through the telescope. Now after mounting the grating, we'll rotate the prism table in such a way that when we observe through this telescope in this position only, we'll observe the image of the white light which we will be observing earlier. The same image will be observed from here, and at that position our prism table is rotated approximately 45 degree, which will be verified by that position. I'll start rotating this. In between you will find the color of the spectrum, where we need to focus for that particular point where your image of the white light comes. It's coming somewhat like this over here. At that position you will lock the prism table. And certain instruments you'll be having exactly the white light, the sharp white light which you are observing earlier, and sometimes you will find in certain instrument over here you will be having feather like curve of the white light instead of sharp white light, but both are correct. Only you need to focus either of them, and at that position you need to stop rotating the prism table and lock the prism table. So you can see exactly the angle of diffraction is approximately 90 degrees. So this position our spectrometer we have aligned for the normal incidence, and then we'll unlock the prism table and bring back into the original position, and again lock that, and again by unlocking the telescope we'll rotate the telescope in this direction to the original position of it, and we'll be locating our spectrum while rotating the telescope, and a certain position where we find our spectrum will lock the telescope. I'll unlock this telescope and I'll rotate the telescope by locating the spectrum. So you will be getting second order spectrum and then the first order spectrum. So you need to go for first order spectrum. Somewhat here I am getting my spectrum, so I'll lock the telescope. Your spectrum will look like this. You can see over here there are 3 red spectral lines, but you will be taking the reading for only one spectral line, and if you go further there will be 2 doublet of yellow spectral line and 2 doublets of violet. So you need to take the readings whatever mentioned in your tabulation. So your spectrum goes from red to violet, and you will be taking the readings from this screw. Once you get the spectrum, you will lock the telescope, and for noting down the readings you will be using this screw. Using this screw, your vertical vertical wire of the telescope will move to the respective spectral colors, and you will note down the readings for each of the window, from each of the window. So you will be taking readings from this window as well as from the another window. So the tabulation for the experiment is, so you will note down the readings in the form which is given in the table. This alpha 1, alpha 2, beta 1, beta 2 is the notation for your windows. Suppose you need to note the reading from both the windows. So suppose you are considering this window as alpha 1 and this window as alpha 2. So you have to uniform with it. In the whole experiment you will consider that as alpha 1 only and this as alpha 2 only, or either this as alpha 1 and this is alpha 2. So suppose you are taking the reading for red spectral line. So this is my alpha 1, this is my alpha 2 reading, which I will be writing in this column, and the same will be following for different spectral lines up to violet 1 and violet 2. After noting all the readings for a particular spectrum, will again unlock the telescope and will start rotating it further in this direction, and you will find the another spectrum of first order on this side of the grating. But the difference is, here in the earlier spectrum we have spectral lines starting from red to violet, and in the next spectrum we will be having spectrum starting from violet to red. In that manner only we will be taking the reading, otherwise the spectrum remains the same only, as I have mentioned and explained in the figure earlier. So now I'll unlock this, and again I'll move the telescope further. In between you will find the white light in the middle position, and then further when you move you will have the spectrum again for the first order. At that position again I will lock the telescope. So the spectrum will look like this. So moving in this direction further, your spectrum now will start from violet. So in this spectrum you will be having first violet line. As you have moved in this direction, the spectrum remains the same from red to violet, but because of the direction you will be noting first the reading for the violet from both the windows, and it will be continued till red spectral line, and you will note the reading again from this screw only. And now for this particular spectrum, again you will be considering a particular notation for the window. So the one which you have considered as alpha 1, say this one will be your beta 1 for this spectrum, and the next window will be beta 2. So again you will note down the readings for both the window for each spectral lines, and you will note down in this column beta 1 and beta 2. After that you will be calculating theta 1, it is diffraction angles, which is alpha 1 minus alpha 2 divided by 2. Similarly theta 2 will be calculating, and the average of theta 1 theta 2 will give me the total theta, and then we will be calculating error in theta, that is theta 1 minus theta 2 divided by 2, and then we will be calculating individually wavelength of each spectral lines, and from the formula that we have mentioned earlier, that is G sin theta equals to plus or minus n lambda. So here our n is the order of diffraction, but what we are seeing is the first order, so n equals to 1. So this will give me the formula for lambda, that is G sin theta by 1, that is n. That only we have used over here for individual wavelength, lambda 1, lambda 2, and then we will be calculating the average lambda 1 plus lambda 2 divided by 2, and then the third table for the experiment is for the calculation of angular dispersive power and the uncertainty in the wavelength. So for that formula is given G cos theta delta theta for uncertainty in the wavelength, and at the last you will be calculating d theta by d lambda, that is your angular dispersive power. And in all the calculation your grating element is 1 by n, that is 1 by 500, that is 2 into 10 raised to minus 3. So in the result you will be mentioning the wavelength of all the spectral lines for red up to violet in the form lambda plus or minus delta lambda, and the unit will be Armstrong, and further you will mention the angular dispersive power d theta by d lambda for all the spectral lines. Some of the precautions which you need to take care in the experiment are the main important one, which I mentioned many times during the experiment, that you need to clamp this or mount this grating very gently. You need not to touch at the center, and the alignment of the spectrometer should not be disturbed throughout the experiment. It should be in a straight line, and the Schuster's method has to be followed in a proper way. And while noting down the readings, you have to use the magnifying lens for avoiding the error. And also you need to take care of the front screws when you are using them, and if you are rotating the telescope, and once you get your final position you need to lock that and further only you will proceed further. And same goes for the prism table. You need to use these screws very gently. So this is the end of your experiment, and then you need to put the grating back and switch off the power supply. After putting back this grating into the box, you need to switch off the light source.